this pre-calculus algebra video, we'll look at the system of linear equations when we're given two variables. If there are two variables, then we need at least two equations. Here's an example of the type of problem you can solve with a system of equations and two variables. Researchers compared college students who were procrastinators and non-procrastinators early in the semester. Procrastinators reported fewer symptoms of illness, but later in the semester they reported more symptoms than their non-procrastinating peers. In this section of the textbook, we'll identify when both groups have the same number of symptoms at the same point of intersection of the two lines. Or in other words, we're going to find out at what point do the number of symptoms come up equal for both groups of students. That's an example of a problem that you could solve using systems of linear equations. Now, this might be new to you, or it might be a review. What I'm going to encourage you to do is write each step really neatly, because these are rather involved and long problems. Not that any one step is that challenging, but when you put it all together, if you make a mistake back in step one, then you're going to find a great deal of frustration that you'll have an entire page of work that's all wrong, all because of one small multiplying or adding error at the very start. So the best advice I can give you as we get started is to check that each step you're doing correctly. After you've done a step, go back and check that it is in fact correct. So for this first problem, we want to determine if the ordered pair that we're given, the ordered pair x equals 2, y equals 3, is a solution of the system that we're given, x plus 3y equals 11 and x minus 5y equals negative 13. Here's our system, and here's our ordered pair, and we want to test whether this ordered pair fits the equation. Here's how you go about doing that. We take our ordered pair, x equals 2, y equals 3, and we replace the x with 2, and we replace the y with 3. And notice this question mark here. What we're doing is checking. We don't know whether it's equal yet or not. We're checking whether it is in fact equal. So here's what that would look like if we multiply that out. 2 plus 3 times 3 is 9. Does that equal 11? Well, 9 plus 2 is 11. Sorry about that. I said 11 and wrote 9. So we're testing. Does 2 plus 9 equal 11? And sure enough, it does. So it looks like for our first equation, x equals 2, y equals 3, is a solution to the equation. Let's check the second equation. When x is 2 and y is 3, we'd have 2 minus 5 times 3, which is minus 15, equals negative 13, and we're trying to test whether this is true or not. Well, if I do 2 minus 15, sure enough, I get negative 13. So because substituting in a 2 for x and a 3 for y in both equations gave us a true statement, we can say that yes, it's a solution. X equals 2, y equals 3 is a solution. Let's check now, let's move on now to see where that 2, 3 could come from. So how do you solve the system to get the answer? Really important that whenever we do these problems, at the very end we want to check. Here's an example that we can solve with a method called substitution. The reason when we look at the system that we know we can use substitution easily is we've got one of the two equations is already solved for a variable. We have y is equal to 3x. So we're going to substitute 3x for y in the equation 1. So our equation 2 was y equals 3x. Equation 1, x plus y, and in place of y I'll put 3x, equals 4. So in place of y, for x plus y equals 4, I'm going to replace the y with the 3x. Once I do this, I can solve for x. X plus 3x is 4x. If 4x equals 4, divide both sides by 4, and I'd get that x is 1. So it looks like we have our 1, and now we want to solve for y. To solve for y, I'm going to go back to this equation 2. Y equals 3x. And I'm going to replace the x with 1. Now that I know that x equals 1, I can replace the x with 1 to get y equals 3 times 1, or 3. So it looks like x equals 1, y equals 3 is a solution. I can check that by plugging those in. When x is 1 and y is 3, equation 1 would read 1 plus, clear those up so you can see those more clearly. We'd have 1 plus 3 is equal to 4, and we're trying to test whether that's true. Does 1 plus 3 equal 4? Yes, 4 equals 4. So it looks like our solution works for equation 1. Let's try equation 2. Does y equal 3x when y is 3 and x is 1? We're checking whether that's true. And it looks like that is in fact true because 3 equals 3. So our solution, we've checked it, and it comes out that the solution is this ordered pair, x equals 1, y equals 3. That's how we can use the substitution method to solve a system of equations. It's not always handed to us so easily with one of the variables solved for. Sometimes we need to use another method called the addition method, or it's sometimes referred to as the elimination method. So we can solve a system of equations with substitution. We can also solve a system of equation with addition or elimination. Here's what we're looking for is we're looking for one of the variables, either the x or the y, that we can eliminate by adding. Now if I add 3x to 2x, that doesn't eliminate the x. Negative 4y plus 3y, it doesn't eliminate the y. You might notice that in order to eliminate or cancel, we'd have to have something like a 3x and a negative 3x, right? If I added those two together, I'd eliminate the x's. So what I need to do is manipulate equation 1 and equation 2, or sometimes it's just to manipulate one or the other so that I can get two opposites. I could do that by seeing that this equation 1 and equation 2 are really close to each other. If I were to multiply equation 1 by negative 2, multiply this equation 1 by negative 2, so here's equation 1. If I multiply that by negative 2, I would get negative 2 times 3x is negative 6x. Negative 2 times negative 4y is positive 8y. Negative 2 times 11 is negative 22. So I would have negative 6x plus 8y equals negative 22. I'm going to stop and double check after I write each step out so that I know I'm not making a huge mistake that I would then need to go back and fix. So for the second equation, what I'm going to do is multiply the second equation by a positive 3. So 3 times 2x is 6x. 3 times 3y is plus or positive 9y. 3 times negative 4 is negative 12. And now do you see that I have the x's are opposites? 6x plus 9y equals negative 12. If I take these two equations now and I add, and here's how I'm going to note it. I'm going to add the, or actually let me rewrite this a little bit. What I have here now is a new equation that was built from equation number 1. So I'm going to call this new equation number 3, and the second new equation is a new equation number 4. So I could take this negative 2 times equation 1 to get equation 3, negative or positive 3 times equation 2 to give me a new number 4, and look at what happens when I add those two together. Negative 6x plus 6x, those cancel out or eliminate. 9y plus 8y gives me 17y. Negative 22 plus negative 12 gives me negative 34. And now I can solve for y. I'll solve for y by dividing both sides by 17. And y is going to equal negative 2. So I've solved for y. I can easily go back to equation 3 or 4 to solve for x. I'm going to take equation 4. So for equation 4, we have 6x plus 9y is negative 12. And in place of y, I'm going to put negative 2. So we have 6x minus 18 is negative 12. Adding 18 to both sides, we'd have 6x equals negative 12 plus 18. Or positive 6. When I divide both sides by 6, I'll get x equals 1. So it looks like the ordered pair x equals 1, y equals negative 2 solves the system. But let's check that before we go on. To check this, I can go back to my equation 1, 3x minus 4y equals 11. And I'm going to put in x equals 1, y equals negative 2, and I'm testing whether this is true or not. So we'd have 3 plus 8 is 11, and it looks like that does come up as a true statement. So our number 1 is good. Let's check number 2. Equation number 2, 2x plus 3y equals negative 4. Let's see what happens if I substitute in 1 for x, a negative 2 for y. I'd have 2, and I'm checking whether this is true or not. We'd have 2 minus 6, negative 4, and that does equal negative 4. So it looks like our solution is the ordered pair x equals 1, y equals negative 2, and it's checked out. That worked. We've solved it, and then we checked it. Number 4, solve the system. X equals 9 minus 2y, and x plus 2y equals 13. When I solve this, I could try this elimination or substitution. I'm going to use a substitution because I can see that x is already solved for. So I could go to equation 2, x plus 2y equals 13. And in place of x, I'm going to put 9 minus 2y. I'm going to substitute in 9 minus 2y for x. When I do this, I'm going to see, let me show this really clearly. By using the associative property, I could rewrite this as, I could regroup this to be 9 minus 2y is grouped together, but I'm going to group the negative 2y plus 2y. And do you see what happens here? That 2y and minus 2y cancel each other out. So we're left with 9 equals 13. When does 9 equal 13? Well, it never does. So what we have here is an example of a solution with, or an example of a system with no solution. There are a few ways we can write that there's no solution. You could just write no solution, or we could write the solution as the empty set, the null set, or we could write an actual empty set. So here's our brackets and there's nothing in it. But notice that this is no solution because we get an untrue statement. Let's try this next one for y equals 3x minus 5. Let's try it again and substituting in, so our equation 2, we could have 21x minus 35 equals 7y. Now in place of y, I'm going to put the 3x minus 5. So now I have 21x minus 35 equals 7 times the quantity of 3y minus 5. And when I simplify that, I get 21x minus 35 is 7 times 3x, 21x, minus 7 times 5, so minus 35. And if I subtract the 21x from both sides or add 35 to both sides, I get this interesting statement, 21x equals 21x. Well, when does 21x equal 21x? Or if you feel better about it, you don't have to do this, but you could divide both sides by 21. But when does x equal x? Pick any number in the real number system. And when is that true? Well, it looks like it's always true, isn't it? X is always equal to x. Or if I had subtracted the 21x from both sides, we'd have 35 equals 35. When is that true? It's always true. Siempre. It's always true. So we could say that the solution is a set of every ordered pair xy such that y is equal to 3x minus 5. Or any set of ordered pairs where it solves one or the other. So I could say this, or I could say set of all xy's, set of all ordered pairs xy's, such that 21x minus 35 is equal to 7y. Or in other words, any ordered pairs that solve one or the other equation will solve them both. So any ordered pairs that solve one will solve the other also. Let's see, oh, it looks like this is a repeat of that first one. So let's go to example number 5. That was number 4. Let's look at number 5, our last problem in the video. It's a word problem. A company has manufactured canoes. We have fixed costs, variable costs, and we have how much they're going to sell these for. So if the cost function is going to be the fixed costs added to the variable costs, we can write this cost function as C of x is equal to $36,000. Where'd I get that? Right from the problem. I've highlighted it in pink. Plus the variable cost is $40 for each canoe that's made, so 40x. Our cost function is C of x equals 36,000 plus 40x. The revenue that we get in green here is $160 for each canoe. So we could say 160 times the number of canoes that are sold. The break-even point is going to be when these two equations are equivalent, when the revenue is equal to the cost. So what we're trying to find is the x that makes the statement revenue 160x is equivalent to cost 36,000 plus 40x. If I subtract 40 from both sides, $160x minus 40x is 120x. So I have 120x equals 36,000. And then I can divide both sides by 120. And if you plug that into your calculator, 3,600 divided by 120, or, you know, we could even do this without a calculator, because I know that 12 goes into 36 3 times. Divide a 0 out from both of them. 12 into 36, 12 3 times, and there's 2 zeros left. So it looks like x equals 300. What does that mean? It means that when x is 300, we're going to we're going to get the revenue and the cost are going to be equivalent. So in other words, when we have 300 canoes, if I go back to replace the x with 300, I can see that the revenue would be $48,000. So we get this ordered pair 300, comma, 48,000. I'm going to leave the comma out of the 48,000 so it doesn't get confused with the comma of the ordered pair. What does this mean? It means that if we produce 300 canoes, our revenue will be $48,000 and our cost will be $48,000 as well. And that's is how we could complete one of these business type problems with manufacturing and cost functions and revenue functions. That's a really important type of example, type of application for solving systems of equations. I want to encourage you to read through, practice some of the other examples that are in our textbook, and if you need further clarification, let me know, or maybe watching that video a second time could help you better understand the cost and revenue functions as well.